The goal of this series of videos is to help you thoroughly understand titrations. We've done enough titration labs together up until this point that you should know the definition of a titration is to slowly mix two chemicals until they've been added in the perfect ratio, meaning there will be no limiting reagent, no excess reagent. This can be called, when you achieve that perfect ratio, it can be called the end point, the equivalence point, or the stoichiometric point. End point, by definition, is when your indicator changes colors. So I prefer that you not use end point to determine whether or not the titration is complete. Because unless you have access to a wide range of indicators, it's very difficult to get an indicator that changes at the pH that you need. For example, the labs we've done up until now, we've used phenolphthalein, which changes at a pH of 8 to 9, but we need to know when the pH is 7, not 8 to 9. Equivalence point and stoichiometric point mean the exact same thing. Stoichiometric point is old vocabulary. If you're using an old textbook or old worksheets, you'll probably see that. So the one I prefer you really know is equivalence point. When you've reached the equivalence point, that means your moles of your two reactants are equal, so you can go through and do the math, apply the stoichiometry. Okay, we are going to come back to section B of your notes in just a couple of videos. What I want to switch to now is our first graph. So let's say we have a container of hydrochloric acid, a beaker of hydrochloric acid, and I'm titrating that with, in this case, sodium hydroxide. Okay, here's your reaction that's occurring. Let's say I have 20 milliliters of my hydrochloric acid and it's a 0.1 molar concentration. I'd like for you to think of this reaction in terms of net ionic. So if you need to pause the video, apply your solubility rules, and think through that process, please do so now. Those of you who are good with solubility rules can look at this and see my net ionic reaction will be such. So I can use math, and the equation molarity is equal to moles over liters to determine how many moles of hydrogen ions are going to be in this beaker. So if I apply my 0.1 is equal to X moles over my 0.02 liters, that's going to give me 0.002 moles of my hydrogen ions. I can then look back at my coefficients from my balanced equation, and I can convert hydrogen ions to hydroxide ions. So this would give me 0.002 moles of hydroxide ions that are needed to react with the H+, to use up all of the hydrogen ions, okay? If I then apply the equation molarity is equal to moles over liters with my hydroxide, and you would have to be given your concentration of your hydroxide. Let's say in this case I tell you it's, we're going to keep the math easy, let's say it's 0.1 molar. So I apply molarity is equal to moles over liters, and you should end up with 0.02 liters or 20 milliliters of the sodium hydroxide solution needed to reach your equivalence point, which I'm going to abbreviate as EP, needed to react with all of the hydrogen ions that are present in that container. So you can mathematically determine where this equivalence point occurs. I would like for you to fill in a graph as well for me. Okay, if we graph pH on the y-axis and milliliters of sodium hydroxide added on our x-axis, the graph of this titration that we've just talked about, where you've got your sodium hydroxide in your burette and your strong acid, your hydrogen ions, because your chloride was a spectator ion, and your HCl is a strong acid, meaning it completely dissociates, or I know something according to equilibrium can never completely dissociate, but K is so high that we can ignore the reverse reaction. So, ladies and gentlemen, if we graph this, we are going to end up with a graph that starts very low, has a very slight positive slope, then we see a drastic rise and it levels off very high on our graph. Okay, what is going on at each point on your graph? So, first point of our graph, I want you to remember that you have hydrogen ions present in your beaker. We're titrating that with hydroxide. So point A on the graph represents the point at which we have not added any sodium hydroxide. So the only thing present in your beaker is your strong acid. So your pH is going to start very low. Draw your line, start your line if you're asked to sketch your graph, super low. Don't leave the grader any doubt as to whether or not you understand that this is a strong acid and therefore will start with a very low pH. Now, as I continue that titration, so I'm going to redraw my 3 hydrogen ions, and now I'm going to add some hydroxide. So I'm going to add 1 drop of hydroxide to this. According to my net ionic equation, the hydroxide will bond to the hydrogen to create water. But I still have excess hydrogen ions in the solution. So my pH still remains very low because I still have strong acid present in the container. Okay? You might see your pH rise just slightly on these graphs. C and B go with the same drawing. You might see your pH rise slightly because of the water that we are creating. It dilutes your solution. So that's why on our graph you saw a very slight slope at the beginning. Okay? So then, ladies and gentlemen, when we get to the point where we have mixed the hydrogen and the hydroxide in the perfect ratio, so I have 3 hydrogens in my beaker. Let me redraw that. And I'm now going to add the perfect number of hydroxides, which in this case would be 3. Each of these would combine, and so the only thing present in my container when I reach the equivalence point will be water. Therefore, for this titration, when I reach the equivalence point, my pH will be 7. For the math, for the example that we used for up above, this would occur when we added 20 milliliters of sodium hydroxide. So if I wanted to choose an indicator to let me know that this reaction was complete, I would need to choose an indicator that changed right at a pH of 7. So it looks like bromthymol blue, phenol red, universal would be good. If you're really good at distinguishing between orange and red, you could use Cresol red. But the point is, you want an indicator that has a color change right at a pH of 7 for this graph. Okay, now what happens if we overshoot the endpoint? What happens if instead of just having the water present, we mix everything in a perfect ratio and we stop? What happens if you continue to add hydroxide? So if I then add hydroxide, I have water and a strong base present. So since I have a strong base, you are going to see your pH rise drastically. So we've gone from a strong acid in the container to having water right at the equivalence point to now having a strong base. So, aha moment. You should now understand why in all of the titration labs we've done so far, you add just a teeny tiny bit and you see a drastic change in your pH. It's because you go from strong acid to the equivalence point, and if you add anything else after the equivalence point, you now have strong base present in that container. For this example, of course, you could flip everything based on what's in the beaker and what's in the burette. So if you have any hydroxide left over, you can add to this very last sentence here. So pH rises drastically after the endpoint because once the hydrogen is gone, you have extra unreacted hydroxide present. So the solution is now a strong base. We've gone from a strong acid to neutral to a strong base. If I go back up to this graph, and you look at the graph, let's go through and label. This right here represents before we've added any milliliters of sodium hydroxide. So this represents A in your notes. Okay, the only thing present in that container is your strong acid, is your hydrogen ions. Through this region here, it's B and C from your notes. You add the hydroxide, it bonds to some of the hydrogens, but you still have leftover hydroxide ions. So you had hydroxide ions present at A, you still have hydroxide ions. You don't have quite as many, but you still have strong acid, so your pH stays low. You might see a slight rise in your pH because we're also creating water, and therefore we are diluting our solution. D in your notes would represent your equivalence point. That is the point at which you've mixed everything in the perfect ratio. There is no hydrogen ion left over in the container. The only thing present in that beaker would be water. For this example, that would occur when we added 20 milliliters of sodium hydroxide. And because the only thing that's present at the equivalence point is water, your pH at the equivalence point should be equal to 7. If we go any further, this represents E from your notes. You now have water present in the beaker, but you also have a strong base, so your pH skyrockets. Okay, the solution is not a buffer. We saw a drastic change in our pH. In one drop, you go from a very low pH to an extremely high pH. So solution is not buffered because you did not have anything present to react with the strong acid and convert it to a weak acid. Once again, if you are asked to sketch this graph, I recommend you practice this. Just get out a sheet of paper and practice drawing these. I would start very low. I would stay low. That last graph, I probably made my slope a little too high. So I stay low with a very slight slope, and then I'm going to have a huge jump, and I'm going to end my graph very high. Okay.